In this video, we will investigate several more problems where we calculate the area enclosed between curves. So first, let's determine the area enclosed between the curves y squared equals 4x, a parabola, and the line 4x minus 3y equals 4. So the first thing I'd like to do here is to just sketch the enclosed region. So let's see here. The first curve, this parabola, y squared equals 4x. Now my pictures don't have to be extremely accurate, but they need to be accurate enough. So y squared equals 4x, that's going to be a parabola opening along the positive x-axis. And the intuition here is to think if you had kind of the opposite situation, if it was x squared equals 4y, you would say, oh, y equals x squared is a parabola opening along that positive y-axis. So we have y squared equals 4x, so roughly speaking, a parabola opening to the right. And then 4x minus 3y equals 4, well, that's a line, and let's just think about what that line would look like. And in order to sketch the line, all we would really need are the x and y intercepts. So we think, well, for the x-intercept, if we were to plug in y equals 0, so if that y term was not there, x would need to be 1. So we have the x-intercept, which is 1, 0. And for the y-intercept, we think if x is 0, what does y need to be? So if the x term was not there, minus 3y equals 4 means y is minus 4/3. So 0 minus 4/3. So roughly speaking, our line looks something like this. And now we see this, nice enclosed area that we would like to calculate. And in the previous problems, when we looked at the enclosed area, it was something that varied very nicely between two functions of y, i.e. we thought of things as being kind of a vertical region. Here, this looks like it varies more nicely in the horizontal direction, that is enclosed between two functions of x. So for that equation of the line, if we solve for x, you would add 3y to both sides and divide by 4. So we would have 4 plus 3y over 4. In terms of the equation of the parabola, if we solve for x, it would be x equals y squared over 4. So the first thing we need to do is think about where these two curves intersect each other. That means we take the two quantities that are equal to x and we set them equal to each other. So y squared over 4 equals 4 plus 3y over 4. So the 4's cancel off. We just multiply both sides by 4. Then bring everything to the left. We'd have y squared minus 3y minus 4 equals 0. This factors nicely as y minus 4, y plus 1. So our points of intersection occur when y is equal to minus 1 and y is equal to 4. So the point of intersection we have here would correspond to minus 1, and the point of intersection above would correspond to y equals 4. So now when we set this up, we're going to think about it slightly differently. We're going to think about cutting it up into horizontal rectangles, so rectangles of this form, and adding up the areas of each one. And if you look at a rectangle of this form, to determine its height, you would need to take the larger curve, i.e. further to the right, larger x values to the right, and subtract away the smaller curve. So mimicking our idea from our previous video, we would say that enclosed area is going to be the definite integral, in this case, over how the y values vary. The y values in our region vary from minus 1 to 4. And what we need to integrate in this case would be the height of that rectangle. So we take the larger curve, 4 plus 3y over 4, and we subtract away from this the smaller curve, y squared over 4, and we're integrating with respect to y. So the new part of the problem here is the sit-up, getting it to here. And the old part of the problem is going to be evaluating via the fundamental theorem of calculus. So pull out that 1/4 that's in common to each term. And then what we are anti-differentiating would be 4 plus 3y minus y squared. Leaving the 1/4 out front and anti-differentiating term by term, we would have 4y plus 3/2 y squared minus 1/3 y cubed. And we're evaluating this from 4 to minus 1. So what that means is we have the 1/4 out front. We need to plug in a 4. So we'd have 4 times 4 is 16, plus we have 3/2 times 4 squared. 4 squared is 16, divided by 2 is 8. 3 times 8 is 24, minus 4 cubed, which is 64, divided by 3. And then we subtract away what we get when we plug in minus 1. So that would be minus 4 plus 3/2 plus 1/3. And if we go ahead and simplify this, plug it into a calculator, what you're going to get back is the number 125 over 24. And this number represents the enclosed area. Now, once again, from a very procedural perspective, how we should approach these problems is first sketch the region, determine how you want to think about it. Do you want to think about it in terms of functions of x, as we've done here, or functions of y, as we've done in previous examples? Find the points of intersection so you know your region to integrate over, and we integrate the larger function, subtract away the smaller function. So let's look at another example. So the first thing to do here is to sketch a picture of exactly what this region looks like. So x equals y squared minus 4y. This is going to be a parabola, and looking at y squared minus 4y, we could simplify this as y times y minus 4, I should say factor. So it's going to cross that y-axis at 0 and 4, and because the coefficient of y squared is positive, it's going to open to the right. So it goes through 0 and 4, and it opens to the right. So roughly speaking, it looks something like this. The other curve that we have, x equals 2y minus y squared, that is also a parabola. Pull out that y, and you see it crosses the y-axis at 0 and 2. But because of the minus in front of the y squared, it's going to open to the left. So if it's opening to the left, and it's going through 2, roughly speaking, it's going to look something like this. So we have the curve that we've just drawn, which is x equals 2y minus y squared, the one opening to the left. And then we have the first curve that we drew, which opens to the right. So I need to determine, what the points of intersections are, at least in terms of the y values, because once again, we see everything works out nicely in terms of functions of y. So we're going to think of this area as adding up areas of rectangles that are horizontal. So to determine where they intersect, we set the two curves equal to each other. 2y minus y squared equals y squared minus 4y. And let's go ahead and put everything on the same side. So add y squared to both sides and subtract 2y. Pull out that y that's in common. Let's say actually 2y that's in common. We'll have a y minus 3 left over, so we intersect at y equals 0 and y equals 3. So the first intersection point we have, graphically we see would be the point 0, 0. The second point of intersection, I don't know what the x-coordinate is unless I plug it in, which I don't need to, but the y-coordinate of that point is 3. So putting this together, the enclosed area, since we're thinking in terms of y values, is going to be the definite integral from 0 to 3, and that 0 and the 3 come from the y-coordinates of the point of intersection. And then what we do is we integrate the larger function, so the one in this case to the right, and we subtract away the smaller function, the one to the left. So 2y minus y squared minus y squared minus 4y. So at this point, let's go ahead and combine terms together and evaluate the integral. So what we are integrating when you take the minus sign and you distribute it through, we are going to have 6y minus 2y squared. Anti-differentiate term by term, so 6 halves are 3y squared minus 2/3 y cubed from 3 to 0. So we plug in a 3, so 3 times 3 squared minus 2/3 times 3 cubed, and we subtract away what we get when we plug in 0. So 3 times 3 squared is 3 cubed, and we are subtracting away 2/3 of 3 cubed, which leaves us with 1/3 of 3 cubed, which is just the number 9. And this represents the enclosed area.